Come on in, everyone. About time to start class. Anybody have any questions while we're waiting for everybody else to show up? You all right? All right, so I guess that's a hold for right now. No one has any questions before we get started? Okay, hopefully everybody got my email as well as Ms. Raskovic's emails, letting you know that our exam will not be until after the break. Some of you may have labs on Monday. If that's the case, then your lab should be on not the Monday immediately when we get back from break, but the Monday thereafter. That's just because the Monday labs are about 1 week behind from everybody else. I'm not sure what the Tuesday labs fall on, so you might want to make sure Miss Raskovic lets you know that one. But other than that, you should be good to go. I will be making up, if I haven't already, I'll be making up a practice test for the midterm, which is the face-to-face test when y'all get back from break. And I'll also, if I haven't already done it, I'll be making up a practice test for the online test. So there will be yet another online test, and in principle, that should, oh, actually, it looks like I've already got that made up. Practice test 4 for chapters 5 and 6. That one's due March 11th, so that's supposed to be like the day you come back, or the day before you, the day you come back, something like that. So make sure you get that one knocked out. That will also help you in doing preparing for the midterm, the face-to-face midterm. So keep all that straight. I know the midterm, or excuse me, the face-to-face midterm that occurs after the break will definitely now include chapter 6, and it might even include chapter 7. Haven't decided yet. Depends on how far we get here. So, anybody have any questions before I move on? All right, well, I have some problems that I wanted to work with regards to gravity just because I gave you the intro and some of the story to gravity, but I didn't really solve any problems. So I figured it might be best to do that. I'm going to give you these problems. They're not necessarily trivial. They cover some big important things, and they're also a little more symbolic than I normally would do, just because the symbolic calculations are sort of the holy grail of the course. What I recommend when you're doing these is if you can't do the symbolic type like I solve for, and like I often do, always just considers, putting in numbers for the actual masses or whatever the variables I have, and try to work it non-symbolically with actual numbers. Then when you get an answer that seems to be consistent with the way that I did it, then maybe try doing it symbolically. So that should help. The first thing I want to start off with, and I'm trying to keep some of the same problems I did for my face-to-face class. So I'm going to start off with question 1. I would like to calculate, whoa, no, I'm going to say calculate G, which is gravitational acceleration, basically. I'm going to share the screen now because I'm so smart I remembered before someone reminded me. Ah, crap, it's asking for a plug-in. Okay, that part's working. Now I got to do this part. Okay. So the screen will pop up in a second on its own. What I'm saying right now is I want you to calculate G for a planet with R equal to 2.00 times 10 to the 6 kilometers, and M equals 9.00 times 10 to the 22 kilograms. Okay, so that's the first problem we want to calculate. Uh, in order to do that, I need to express something that hopefully you've already figured out, but if you didn't, that's okay. It's not that big a deal. I made some allusions to it during class, but I hardly completely taught it. So I want to show you exactly how we reach this conclusion. So I'm going to write solution. And you may go ahead and type your first and last name into the chat so I can have you for attendance. If you leave early, that's on you. It's okay. So I don't worry too much about it. I just want to make sure you guys have the opportunity to check out everything. So the first thing I want to remind you is that we did already discover a formula for the force of gravity on an object. Does anybody recall what the formula is for, let's say, me having a mass m? What would be the force of gravity acting on me at the surface of the Earth? Anybody recall that formula? It was a W word. You can say it or type it, either one. Looking for a W word. That was what we used for the force of gravity acting on an object. Very good. Yes, it's the weight. Does anybody remember the formula for the weight? Very good. Yes. So weight is actually equal to mg, but now we've also learned that the force of gravity is equal to g m1 m2 over r squared. So I'm going to set these two equal to each other and say m times g is equal to the gravitational constant of the universe times the mass m of the object whose weight we were just talking about, times the mass of Earth, because in this case we're actually talking about the gravitational acceleration on planet Earth, and then we're going to divide that by the radius of planet Earth. Now, you might think that's weird, Mr. Younger. You're using the radius of the planet, not necessarily the distance of the person of mass lowercase m from the center of the Earth. Does anybody have any idea why I'm not making a specification that that R down there should actually be the distance from the center of the Earth to the actual person whose mass is lowercase m? Anybody know why that's not being done? Or some alternate explanation? All right. So in reality, we sort of are, but the thing is, the radius of the Earth is really, really huge. So if we were to take the radius of the Earth, which is like 6.38 times 10 to the sixth meters or something around there, and then we added to it the elevation above sea level, which is, we're assuming the R of the radius of the Earth is roughly from the center of the Earth to sea level. If we add the distance that we are above sea level or the distance below sea level, if we subtract that from the R, what you'll find out is the digit, the first digit, the biggest digit on our altitude will in fact be way, 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 way smaller than this R. So, unless you have a screen on a calculator that's really big that can take like, 6 or 7 digits, you won't even be able to see where that number is. So that's why we can roughly say it's R. You can see that there's 2 extra credit assignments at the bottom of week 8. I highly recommend you check those out and try to do them. That'll give you a little bit more understanding. But now that we've got that filled out, we can now tell that the lowercase m cancels out in this. And ultimately, what we've decided is that g for any planet is equal to the gravitational constant times the mass of the planet divided by the radius of the planet squared. So that's the more general result. With that in mind, we can go ahead and try to solve it. So I'm going to say G for this planet is equal to the gravitational constant times the mass of the planet divided by r squared. Now, if you're curious, if you look at episode 1 of The Next Generation, you'll see that John DeLance comes in, and he's Q. So he's supposed to be a godlike figure in Star Trek. And later on in a future episode, he's asked by Geordi LaForge how might they might fix a problem where like a black hole's pulling them in or something like that. And he said, "Oh, easy, just change the gravitational constant of the universe." So you can see people making use of such things in Star Trek and other science fiction stuff as well. So I just thought I'd point that out. Now we're going to go ahead and do the calculation with it. Now the gravitational constant is something that was determined experimentally, and it's essentially 6.67 times 10 to the negative 11. And that unit is Newton meters squared per kilogram squared, which I think you can tell from the formula for gravity that that's exactly what you'd expect it to be. Now, in this case, we're actually using the mass that we were given, which is 9.00 times 10 to the 22 kilograms. Notice that kilogram cancels out with one of the kilograms in the G. And now we're also going to take this and divide it by r squared, and R was 2.00 times 10 to the 6. So I'll write 2.00 times 10 to the 6. And that one's supposed to be kilometers. Uh, we're actually supposed to have that in meters. So I'm going to kill this 10 to the 6 and make it 10 to the ninth. So times 10 to the 6 kilometers would be 10 to the ninth meters. And that's because the units within the SI system, basically when you're using any equation for the SI system, they're expecting you to put the distance in meters, the mass in kilograms, and so on and so forth. So we actually want to make sure we do that. Now I'm going to calculate this. Whoa. And calculate this with my calculator. And you guys should, of course, try to do the same thing on your own calculator to make sure I don't make any careless mistakes. So I'm going to take 6.67 e to the negative 11. I'm going to multiply that by 9 e to the 22. And then I'm going to divide that by, I'll use parentheses, so you don't necessarily have to. You just need to be careful. I'm going to put 2 e to the ninth, and then I'm going to square that quantity. And when I do this, I get 1.50 times 10 to the negative 6 meters per second every second, which is a minuscule, insignificant amount of gravitational acceleration. In fact, I'm wondering today if I might have forgot the exponent that I did before. Let me check again. 10 to the 22 over 10 to the ninth. Yeah, I guess that's about right. So that's the actual answer for this gravitational acceleration. Anybody have any questions on that? So now I'm going to up the ante a little bit and try another problem. Anybody have any questions on this one before I move on? Okay. What I want to know now is A, what is G for a planet with M equal to the mass of the Earth? Remember, that's the symbol for the mass of the Earth is that little circle with a plus sign inside of it. But with R equal to 3.00 times the radius of the Earth. So that's part A. And then part B is what if M is equal to 3/4 the mass of the Earth and R is equal to 2.00 times the radius of the Earth. Okay, so that's our big questions here, and I'm going to show you a good way to do this so that you can actually get exact answers symbolically and you get to do a lot less calculating, that sort of thing. So let's get cracking on this. Solution. Feel free to stop me if you don't understand anything. What we do know is that G, that we know of from Earth, is in fact the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. Therefore, we can write G for the planet, which I'll call G sub P, as being equal to the gravitational constant of the universe. Then I've got for part A, let me specify that. I'll call this A. And I just did it purple so you could see that I'm actually changing a little bit. In this case, we're talking about in part A, the mass is exactly the same as the mass of the Earth, so I'm just going to leave the mass of the Earth there. But what will be different is the radius of the planet is going to be 3.00 times the radius of the Earth. Of course, that quantity is squared. So you end up getting 1/9.00 times G times the mass of the Earth over the radius of the Earth squared, which I think you can see is in fact equal to 1/9.00 times 9.80 meters per second every second. In other words, this quantity right here, that is G as we know it. And I definitely hope you'll be curious enough that you'd actually do that calculation yourself. I think when I divide this 9.8 by 9, I think I get 1.089, but I'll double check. I'm going to turn the calculator on this time when I calculate it. I'm thinking that's going to work a little better. Let's try. Yep, it did. It worked a lot better that way. So, and I was remembering correctly, the answer is 1.089 meters per second every second. So that's the actual gravitational acceleration for this new planet that we're talking about. So for part A, I'm just going to write this down. I'm going to say A, G planet is equal to 1/9.00 times G, which is 1.089 meters per second every second. And I'll box that off with a nice red box. Any questions on that one? Hopefully that makes sense to everyone. Now for part B, I'm actually letting both things change. So let's do part B. I'm going to write that in purple again just to remind us that I'm doing another part. And this time I've got G planet is equal to G. Now this one we actually are allowing the mass to change. So it's going to be 3/4 times the mass of the Earth. And all that will be divided by, instead of 3 times the radius of the Earth, this one's going to be 2.00 times the radius of the Earth squared. And I think you can see that when I square that in the bottom, the 2 squared becomes 4, and the 4 times the 4 in the denominator of 3/4 gives me 16. So I end up getting 3/16 times G, darn it, 3/16 times G times the mass of the Earth divided by the radius of the Earth squared, which is 3/16 of G, which is 9.80 times 3, and then divided by 16 gives me 1.8375. And I'm carrying way more sig figs than are really necessary, but that's mainly to make sure you all can compare it to as many digits as you get so that you can make sure you did it correctly. So that is the actual gravitational acceleration of the planet for part B. So I'm going to box that off in red. Anybody have any questions with that one? All right. So those are some of the quote unquote easier problems. You should know that gravitational acceleration, the 9.80 that we use, is really just the gravitational constant times the mass of the Earth divided by the square of the radius of the Earth squared. Actually, I said squared twice, so I think you know what I'm talking about. But anyways, let's try another problem now. Now, this one is one that I didn't get a chance to do anything like it for you, and I really wanted to. So this is one where we're going to actually have to calculate a magnitude of a force and then make it into a vector. So this is a more advanced skill, but it's definitely a skill you're expected to know upon taking this class. So in this case, I'm going to go ahead and draw what I've got going on here. So I'm going to have a coordinate system like this. Oops, not that line. I want this coordinate system to be like this. Okay. This is going to be my x-axis, and this is going to be my y-axis. And right here, I'm going to have a mass m. And then I'm going to go over to right here, and I'm going to have a mass of 4m. And that distance right there is going to be called x0. And then I'm going to have another mass up here, and this one's going to be 3. Oh, excuse me. Sorry. 3m. And this distance is going to be y0. And then out here, I'm going to have a mass, and this one's going to be 2m. Okay. And what I want to know is what is the total gravitational force on mass m. Okay. So in other words, I'm trying to compute the total force on the mass little m. And what we should know, hopefully we already know it, is this. The force on M, the total force, is actually the force on M due to 4M. So I'll put a comma there. Plus the force on M due to 2M. Plus the force on M due to 3M. Like that. So that's just our rule that we learned about when you're adding forces. Forces are vector quantities and you have to add them If you need the total force acting on something, you have to take each force acting on it and add them up vectorially, and that's what we're doing. So I'm going to start off with the easy guys and just using the formula. Remember, the formula for Newton's law of gravity is that F is equal to G times M1 times M2 divided by R12 squared. Now, we also got to remember the rule that went along with it because Newton not only gave us a formula for the magnitude, he gave us a descriptive way of telling us how to actually find out its direction. And what that was that R12 is the distance between the center of a mass of the object whose mass is m1 and the center of the mass of the object whose mass is m2. Again, that if you imagine a little line from the center of mass of M1 to the center of mass of M2, the length of that line would be R12. And in fact, the vector force will be somewhere along that line. In other words, it'll be parallel to that line. And we got to remember that gravity is always attractive. There's no repulsive forces. So I'm going to start off with a couple of the simpler ones. So let's start off with, let's say F m comma 4m. Okay. So the magnitude of this will, as always, be the gravitational constant. But now I've got m is one of the masses and the other mass is 4m. So I'm going to write this as m times 4m. So I literally mean when I say the mass is 4m, I literally mean the symbol 4m represents a certain number of kilograms. So for instance, if m was 100, then 4m would be 400, 2m would be 200, and 3m would be 300. Can anybody tell me the distance between m and 4m? Evidently my chihuahua can, but he doesn't speak very well. Very good. That's right, Infinity. So yes, the distance between m and 4m. Notice these are drawn as little dots, so they really are pretending like they're point particles. So I'm just going to put a x0 in the bottom and make sure I square that. And now I can make that a little more straightforward by just saying it's 4 times gm squared over x0 squared. Let me give you a few choices. I would like to know what direction is this force or excuse me, FM4M? Which direction is it pointing? Is it pointing to the left, to the right, up, down, or diagonal? Anyone? The choices are left, right, up, down.
Right?
So you're saying that it's pulling M to the right, and you'd be exactly correct. Yes, because remember the forces are always attractive. So what you should be thinking in terms of is the M is being pulled towards the other mass, and that is to the right. So I can actually make this a little easier than you might think by saying that F M comma 4M is actually equal to 4 gm squared over x0 squared, and it's going to point in the I hat direction because the I hat direction is pointing to the right. That makes sense? All right, you guys try to do FM3M. I'm going to do it as well, and we'll see if we get the same answers. So what you're trying to do now is FM comma 3M. Calculate the magnitude and then see if you can go ahead and figure out what the actual direction will be and make a vector out of it. So you try it. I'll do it with a slight delay, and then hopefully we'll all have the same answer. Hopefully everybody got that for the magnitude, just like I did. And now let's see if you can come up with the direction as well. Anybody have any problems getting the answer that I just wrote down? Anybody have any questions on how I did that? All right, now next, I've got to find the force between M and 2M, and I just drew a diagonal line. Uh, Remember the line that connects the 2 point masses or the centers of mass of the two masses? Uh, Along that line is the direction of the force. So somewhere along that diagonal that I just drew, the force has to act along that either down and to the left or up and to the right. Anybody have any idea which way it should be pulling? Yep, up and to the right. Very good. So yes, again, M is attracted to 2M, so you should imagine M's being pulled up and to the right. And in fact, you can even picture it like this. That's the force. So this would be F M comma 2M. And notice I've got it attached to the lowercase m. Similarly, obviously these forces are not to scale. This would be F M 4M, and this would be F M 3M like that. And in fact, I'm going to make use of this little angle right there, theta. Okay. So the magnitude of FM2M, you guys should try to figure this out as well as I go. So I'm going to go write it down, and I want you guys to think about it as well. Hopefully you can think about and have the answer even before I write it. I'm going to write this. Hopefully everybody was able to see that that in fact would be the magnitude. And that's going to be 2GM squared over x0 squared plus y0 squared. I'm going to go a little further and say that theta is equal to the inverse tangent of y0 over x0. And that allows us to make a little triangle, which is x0, y0. And it's a similar triangle, so it has that same angle theta, but this side right here is x0 squared plus y0 squared. And what we have to see is a similar triangle, which it looks like I made that a little bit bigger than 3 by 3. So I'm going to say I'm just going to go from here to here, say. This would be the x component of the force, and this would be the y component of the force. So this would be F M 2M Y, and this would be F M 2M X like that. And this would just be the magnitude F M 2M. And this would be the angle theta. So I think you can tell that FM2MX is just going to be FM comma 2m cosine theta. And then, of course, I'm going to have to multiply that by I hat because it should point to the right. And similarly, this one's going to be Fm 2m times sine theta, and that was going to be pulling upwards, so I'm going to say that is times j hat. Does that seem reasonable to everybody? Anybody have any questions about how we got that? Okay, so what that means is F m comma 2m is going to be, notice we're always going to have a gm squared, so I'm just going to pull that out in front and just say gm squared. And then I'm going to put a curly bracket right here. And I'll notice that what I have for the x component, which would be this guy, okay, that also is going to group up with my x component here. So for that top one, I'm just going to get 4 over x0 squared. Oops. So I'm going to get 4 over x0 squared. And then for the other part, I have to take the 2 over x0 squared, y0 squared, and multiply that times the cosine of theta. If you look at this triangle right here in the bottom right, I think you can see that cosine theta is equal to x0 over the square root of x0 squared plus y0 squared. And of course, I already had a x0 squared, y0 squared in the formula for the magnitude, so that's going to make it to the 3/2 power. So for just the x component as a result of the Fm2m, I am going to get 2 over x0 squared plus y0 squared, all that to the 3/2 power. And all that will be times I hat. Now I'm going to do the same thing. I've taken into account the x's. Now I've got to do the same thing, but with the y's. So now I want to take into account this guy and this guy right here. Okay. So I still have the gm squared out in front. Now I need to put my square bracket, and my square bracket is going to start off with the Fm3m. So that's going to give me 3 over y squared. That's 3 over y0 squared. Plus, now I'm back to doing the Fm2m. And that one, of course, had a multiplier of 2 out in front. But now, oops, and I left off something in here. This is supposed to be x0 there, because remember cosine had an x0 on the top, so I just neglected to put that in. The units wouldn't have worked if I didn't do it right anyways. So the same thing happens here when I take the sine of theta. I get y0 over that same square root like this. So again, this one's going to become 2y0 over x0 squared plus y0 squared to the 3/2, and then all that would be times j hat. And then we've got the right hand curly bracket. And that's it. That's pretty much as simplified as we can get. I'm going to write out the full answer down below just to make it a little clearer and bigger. So the full answer is going to be Fm And actually, that should have been what I wrote on the right. Notice here I wrote FM2M. That's not correct. That was just supposed to be FM because I was adding everything. So FM here, glad I caught that now, but anyways, FM here should actually be G times M squared. That a student just came in, or probably was bumped out by accident. Now my square bracket is going to be 4 over x 0 squared plus 2x 0 over x 0 squared plus y 0 squared, all that to the 3 halves. And then that will be times I hat. And then plus another square bracket. This time it's going to be 3 over y0 squared plus 2y0 over x0 squared plus y0 squared to the 3 halves. And all that will be times j hat. And that should be the whole answer. Anybody have any questions on that? So this might be a little daunting just because it's all symbolic. There was no numbers being used in there hardly at all, that kind of stuff. If that's the case, don't fret it. This is next level stuff that you would ideally like to do. So all you have to do is pretend m's going to be, 10 to the 10th. Let's say m is 1 times 10 to the 10th kilograms, and then of course 4m would be 4 times 10 to the 10th kilograms, and then 2m would be 2 times 10 to the 10th kilograms, and 3m would be 3 times 10 to the 10th kilograms. Work out all this stuff just like I did. You can use this as a blueprint of how to do it, only you're actually using numbers instead of symbols. You can take x0 to be, I don't know, 4 meters, and y0 to be 5 meters if you want. That'd be fine. Work it all out, and then try doing it with the symbols, and maybe that'll make you more proficient. If you don't, that's okay. You've got 2 semesters to learn this, maybe 3 if you go to another place where they're requiring 3 semesters. So the main thing is, can you do it? And ultimately, it would be great if you could do it symbolically, but if you can't, that's not a deal breaker or anything like that. So, anybody have any questions on that? Anything anyone didn't understand about how we did it? Okay. Well, I have another problem as well, and this is another one that's sort of vector related, so I want to do it as well. I'm going to draw a coordinate system again. Let's say this is my coordinate system. Okay, I'm going to say this is my y-axis and this is my x-axis. And what I'm going to do is imagine going up a distance r to a mass big M, and then go down a distance r to a mass big M. And then imagine going to the right a distance x. And there we'll have a mass of little m. And what I want to know is, or actually what I want to do is show that F on M is the formula they're giving us is 2G big M little m x over x squared plus r squared to the 3 halves power. Okay, so that's really the problem they want us to solve. What I'm going to do is let's take these blue lines and I'm going to map them out a little bit so you can see that this is one line along which the forces should be acting. Actually, I drew this one off a little bit, so I'm going to correct it. Oops. I'm going to dang it. Keeps erasing. I'm going to correct it and say it's right along here. Let me fix that. And now let me further fix it. When I want to erase it, I can't get it to erase for nothing, but there it is. Okay. So what we see here is that in this particular scenario, lowercase m is going to be pulled down into the left by the lower mass, and it's going to be pulled up into the left by the higher mass. And something very specific happens. Specifically, we can see that we're going to have an x component of force going this way, which is the negative x direction, and then a y component of force going this way. For the other one, we're going to have sort of the same thing. The x component is going to go this way, and the y component is actually going to go it'll be the same size, but it's going to be in the negative direction. So I think from the symmetry of this problem, you can probably see something to make the problem a little easier already. Does anybody see any symmetries that might be able to help us here? So what we're going to have to do is we're going to have to use the formula, Newton's law of gravity, to calculate the magnitude of this force up here, which is F m m top. And then we're going to have to use the same equation to calculate F m m bottom. And then we're going to have to use our understanding of trig functions, for instance, to calculate the x components and the y components of those vectors, and then add x components to x components to get the new x component, add y components to the y components to get the new y component, and then the sum of all that better have a magnitude equal to this. So now that I've stated that, can anybody think of any symmetries or anything that might make our job a little easier? Okay. So one of the symmetries, since no one's answered any yet, one of the symmetries is that phi is going to have to equal theta, and that's because the opposite over the adjacent for phi is actually r over x, and then the opposite over adjacent for theta is again the r over x. Now you can tell clearly the r is negative in the theta case and the r is positive in the y case, but the magnitude is going to be the same thing. So we definitely have theta and phi are the same thing. Anybody see any other symmetries? How about this? The f lowercase m uppercase m sub t sub y is equal to the negative of f lowercase m uppercase m b sub y. that implies Fm total sub y is equal to 0. So that's the symmetries I was shooting for. First off, once I showed that theta and phi were equal, then that forced us to reach the conclusion that the y component of the bottom one is the negative of the y component of the top one. And since they're equal but opposite, when you add them, you're going to get 0. So all I really have to calculate is the actual x component. So I'm going to calculate the magnitude, and then I'm just going to multiply it by cosine phi or cosine theta, and that'll give me the x component. Then, of course, I'll do it for the other one and then add them. So let's write F M capital M T is going to be equal to, we've got a G, we've got a big M, and we've got a little m, and this is for the top one. So I am going to just take the magnitude for right now, and GMM over the distance between them, and the distance between them from the Pythagorean theorem should be x squared plus r squared. This implies that Fm big M T sub x is equal to G big M little m over x squared plus r squared times the cosine of phi, which is G m m over x, x squared plus r squared, like so. And then the cosine of phi is adjacent over hypotenuse, so that's just going to be x over the square root x squared plus r squared. So that's what the x component is for the top one. For the bottom one, we'll calculate the magnitude again. That's lowercase m, uppercase M. Now I'm going to put a bottom there instead of a top. This is going to be G M M over. There's a delivery person here, Shawnee. There's a delivery person here. This is going to be x squared, just trying to save us the raising of the heck from the puppies. So r squared. So that's the actual magnitude. Now to get the x component, I'm just going to take lowercase m, uppercase M, bottom, and put an x subscript on it. And that's going to be G M M over x squared plus r squared times cosine theta, which gives me G M M over x squared plus r squared times x over square root x squared plus r squared. So now I just got to add those two and we'll be done. So I finally see that Fm, and I'll call that Fm total, is in fact just the sum of those two. So I'm going to say it's G times big M times little m. Notice both of them have an x, but I have to add them together, so it's going to be a 2 times that. And then the denominator is going to be x squared plus y squared, or excuse me, x squared plus r squared times the square root of x squared plus r squared. So that gives me x squared plus r squared to the 3/2 power. And that's what we were asked to do, and we are done. Anybody have any questions on that? Does that make sense to everyone? All right. Well, there's a kind of neat little simple problem, and this is a Kepler's law problem. So I'd like to work it, and this one will be pretty simple. Uh, what I'm going to do is I'll say Neptune has a semi-major axis of A Neptune equals 4.5 times 10 to the ninth kilometers, while Earth has a Earth equals 1.5 times 10 to the eighth kilometers, and Halley's comet has Halley's comet equals 76 years. So part A, what is the orbital period of Neptune? Oops. And B, what is the semi-major axis of Halley's comet? Oops, let's write that a little better. So that's what we're going to try to solve. Everybody understand the problem? Anybody have any questions? All right, so what we learned from Kepler's third law basically said that the square of the period is proportional to the cube of the semi-major axis. Okay. Now, I mentioned this in class last time, so I want to reiterate it. Uh, Pluto, though it's not a planet anymore, according to our new definition of the planet versus Plutoids and dwarf planets and that sort of thing, it still has the most elliptical orbit of all the orbits of the large bodies that are, normally considered planets are Pluto. Okay, so it's the most elliptical one, but still, if I were to, walk into the classroom and draw an exact model of Pluto's orbit and then put a circle of about the same size next to it and not tell you which one's which, you couldn't just look at them and tell which one's the ellipse and which one's the circle. Well, unless you had a really, really, really good eye, you probably couldn't. And in fact, you probably need to do some measurements to actually figure it out. So that gives you an idea of how really circular these elliptical orbits are. So a lot of times, like in the extra credit that I've assigned you guys, you can set G M1 M2 over R squared equal to MV squared over R and get a version of Kepler's third law. That's what one of the extra credit problems is. And the reason why I can do that is because they're so close to circular orbits, it's not going to make a huge difference. But it did make enough for Kepler to recognize that it was something different. So we're going to start with that. And one thing, hopefully, you recall from, high school algebra 1, high school algebra 2, was that when you have a proportional, like here with the little fish symbol, when you have a proportional statement like that, it can become an equals just by adding a constant. So what I'm going to say is therefore t squared is equal to some constant times a cubed. So now you can see that maybe the reason I gave you information about Earth was so that you could determine what actual K is. And once we know K, then we can answer all these other questions. And that's exactly the case. That's what we're going to do. So we can see that K is actually equal to t squared over a cubed. And we were given that the semi-major axis for the Earth is 1.5 times 10 to the 8th kilometers. Now, I've told you before, you're really supposed to be using meters, but everything I've got here is in kilometers. So I can use it, and I just have to remember that the answer is going to come out in kilometers or whatever unit of time I have. So in this case, I'm going to put the kilometers in there and say that's okay, but I got to remember to raise it to the third power. And then I also need to know for Earth, what is the period of the Earth's rotation? Anybody know that off the top of their head? Excuse me, not rotation, revolution. What is the period of the Earth's revolution? In other words, what's the orbital period of the Earth? Yes, very good. Basically a year, which is 365 days. I'm going to show you something that can come in handy. The period for the Earth is 1 year, but I really want this to come out in seconds. So there's this neat little thing I can use, which basically says pi times 10 to the 7th is the number of seconds per year. I'm going to show you that with the calculation below, but for right now, that's what I'm going to do. This will force it to come out in seconds squared over kilometers to the fourth power. But I will, like I said, justify that that's approximately pi times 10 to the 7th. So first off, I'm going to do 1 times 3.14 e to the 7th. So that's what I put in for the top. I'm multiplying those two, and now I'm squaring that. And that's going to give me 9.8596 times 10 to the 14th. And that comes out in seconds squared. Now I'm going to take 1.5 e to the 8th, and I'm going to cube that. And that comes out to 3.375 times 10 to the 24th kilometers cubed. Now, if I divide these two, I get 2.921, which is way more sig figs than I really need, to be honest with you. So that's 2.921 times 10 to the negative 10 seconds squared per kilometer cubed. So that's what our K is. We have that. Now, let me take a short break and show you exactly how I got that pi times 10 to the seventh. So 1 year, which when you're converting units, you can go ahead and put it over one so you don't get confused what's the numerator and what's the denominator. And what I'm going to do is I'm going to say 1 year on the bottom is 365.25 days. And then I'm going to say 1 day is equal to 24 hours. And then I'm going to say 1 hour is equal to 3,600 seconds. And when I'm done with that, you'll get 3.155 times 10 to the seventh. And that's seconds. Okay. So you can see essentially where it came from. Okay. Obviously, it's 3.14 is what we use because that's roughly what pi is, 3.14159. But it's off in the or in the second decimal place or in the third sig fig. So that's really plenty close because we're mostly given two sig figs here anyways. Now that we have that, we can use this K and realize since Neptune, like Earth, is also orbiting the sun, it has the same K. It also works for Jupiter, Saturn, Mercury, Venus, Mars, uh, most things orbiting in the asteroid belt, most things orbiting in the Kuiper belt, most things orbiting probably in the Oort cloud as well. So let's go ahead and figure out part A. So now that we have part A, we're supposed to be looking for the orbital period of Neptune. So I'm going to say T Neptune is actually going to be equal to, we see that we have T squared equals KA cubed. So I'm going to say T is equal to the square root. Okay, I'm just going to erase a bunch of stuff at random because my thing aggravates me. So I'm going to say T is equal to a square root of K times A cubed, where A is the A for Neptune. So I'm going to say that. Now I'm going to put in my constant, which is 2.921 times 10 to the negative 10 seconds squared per kilometer cubed. Now I've got to take the A for Neptune, which is 4.5 times 10 to the ninth kilometers, and I got to cube that, which is good because notice if I cube it, then it'll cancel out all the cubic kilometers in the bottom and just give me a square root of s squared, which is in fact s. Okay, so I'm going to take this 2.9 times 10 to the negative 10th, and I'm going to multiply that by 4.5 e to the 9, and then I'm going to raise that to the third power. And that's going to give me a square root of 2.662, carrying way more sig figs again, times 10 to the 19th second squared under the square root. And so I'm going to raise that to the 0.5 power. And that gives me 5.2, which is really all the sig figs I'm supposed to have. 5.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the ninth seconds. Now, I really don't want this in seconds. In fact, I'm going to use it in years to help me. So I'm going to say times pi times 10 to the seventh seconds is equal to 1 year. Okay, so I'm going to divide this number by 3.14. I'm actually typing in 3.14, even though I know it's 3.155 e to the seventh. And this gives me 164 years. Any questions on that one? No questiones? All right, let's try B now. So B, we're wanting to figure out something about Halley's Comet, and this time they gave us the period, so we're wanting to solve for the semi-major axis. So for this, what I'm going to do is I'm going to take that same equation, which was t squared equals ka cubed, and now I'm going to say a is equal to the cube root of t squared over k. So this is going to be equal to the cube root of, now I'm going to type in 76 years, but again, I'm going to say times pi times 10 to the 7th seconds per year. And then all that's going to be squared. And then I'm going to divide by k, which was that 2.921 times 10 to the negative 10th second squared per kilometer cubed. So notice what's going to happen. We're squaring the seconds. That's going to make second squared. That's going to cancel out the second squared in the bottom. But in the bottom, there's a denominator that's kilometers cubed. So that's going to come to the numerator. And the cube root of a kilometer cubed is a kilometer. So this does actually give us the units we want. I'm going to go ahead and try to compute it. First off, I'll write the third root or the cube root again. I'm going to take 76 times 3.14 e to the 7. And now I'm going to square that. And that's going to give me 5.69 times 10 to the 18th. And that's seconds squared. All that's going to be divided by 2.921 times 10 to the negative 10 seconds squared per kilometers cubed. Okay, that turned out really badly. Okay. So I'm going to take that 5.69 times 10 to the 18th. I'm going to divide that by 2.921 e to the negative 10. And I get the cube root of 1.95 times 10 to the 28th kilometers cubed. I'm going to raise that to the 0.3333 power. And that gives me 2.7 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th kilometers. So the semi-major axis for Halley's Comet, A sub, ooh, that was an ugly A. A sub Halley's Comet is in fact equal to 2.7 times 10 to the 9th kilometers. Anybody have any questions on that one? All right, we got about 5 or 6 more minutes left. There's a problem your book does, and I like it. Not only that, I like it because it shows us a way to use something that we often have to use. It's called the binomial theorem. But in general, you should be able to use any Maclaurin or Taylor series expansion to, for instance, alter the way something's written so that it can make more sense, or you can examine special cases for, R less than X and stuff like that. So let me start off by saying that 1 plus or minus X raised to the n power, according to the binomial theorem, is supposed to be 1 plus or minus n times X plus n times n minus 1 over 2 factorial x squared, plus or minus n times n minus 1 times n minus 2 over 3 factorial x cubed plus dot dot dot. So that's the binomial theorem. And normally uh, we might use two terms. Sometimes you might use a third. Sometimes you might use a fourth maybe. But generally speaking, it's almost always just two terms. Okay. But what I would like to do is calculate delta G, which is the gravitational acceleration at an altitude or a distance from the center of the Earth equal to r plus delta r minus G at just plain r. Okay. So what we know is G, I'm going to just say this is the question. So I'm writing it like that, is what's that? So I'm going to go with G is equal to Gm over R plus, or excuse me, over R squared. So from that, I'm going to say G sub R is G M over R squared, and G sub R plus delta R is going to be G M over R plus delta R quantity squared. Everybody follow what I've done so far? Make sure you ask me questions if you have them. Okay. So now I'm going to calculate delta G, which is, like I said, G of R plus delta R minus G of R. So this is going to be, notice there's a common factor of Gm for both of them. So I'm going to go ahead and pull that out in front. And then what I have is 1 over R plus delta R squared minus 1 over R squared. Now, at this point, I can go ahead and factor out a R. It's kind of weird, but I can do it. So I'm going to say Gm over R squared because I know I can factor it out. What's going to happen is I factor out the R from the R plus delta R in the bottom, and that's going to give me 1 plus delta R over R like this. And that whole quantity there would be squared. And then this quantity is going to be just minus 1. So I'm now going to write this as Gm over R squared times parentheses 1 plus delta R over R. Actually, let me change my bracketing a little bit. I'm going to change my bracketing to curly bracket and then square bracket. And now I can say all this is going to be to the negative 2 power and then minus 1. Okay, so now I've got it more or less in the binomial theorem format. So what I'm going to do is use that. Remember, this is 1 plus x to the negative 2 power. So I'm going to say 1 plus or minus. Now, the n in this case is actually a negative 2. So I'm going to have to say minus 2 times delta r over r. And then there could be some other terms, which I'll say plus dot dot dot, but I don't really need them because I see what's going to happen already. I've got a minus 1 there. And with that minus 1 cancels out with this plus 1 like that. So ultimately what I get is delta G is equal to negative 2 G delta R over R. And that's the formula we were actually shooting for. And hopefully that's enough of showing you how to use the binomial theorem to make some sense of things. That's it. You can look in the end of chapter 6, and there's two problems that I think are worthwhile, number 76 and number 25. You might want to check those out, but while you're in there, you'll see one that has exactly this answer, delta G equals negative 2G delta R over R. So you can use that to see that we are doing sort of problems that your textbook expects. Uh, but that's it. Everybody, time is up. You guys are free to go. Make sure you chat me your first and last name. Hopefully you've already done that, but you're free to go, and I will see you Wednesday. Thank you.
Thank you. Have a good night.
You too, Jacob. That looks like it's it. No one else is here. Bye, everybody.